Welcome to the Summer Seminar Series again. This week's speaker is Mary Hudson, and I know that everybody knows her, or almost everybody, but I'm still going to introduce her. She deserves an introduction as everybody else. So Mary is a professor at Dartmouth College in the Department of Physics and Astronomy. This is a department which she actually chaired for 8 years. She's a California native, and she spent 10 years at UC Berkeley after her PhD at UCLA. She is a fellow of the American Geophysical Union and a recipient of the McElwain Award. And Mary gave the A.G.U. Van Allen Lecture in 2006 and received the American Institute of Aeronautics and Astronautics James Van Allen Space Environments Award in 2012. She is currently a co-chair of the NRC Committee on Solar and Space Physics, and she has served on the Heliophysics Decadal Service Steering Committee too. And Mary is an affiliate scientist at HAO. She's been so since 2010. She religiously visits Boulder every summer, and she loves hiking. So with that,
okay, thank you very much. Yeah, I told Rebecca that you could really just say same as last time. But I very much appreciate the invitation always.
Hey, Rebecca, why don't you turn the podium mic off?
Yeah, there's a little feedback thing going on here. Yeah, thank you. Okay, so I'm going to talk today about, is this going to work?
I'll get ready.
I can just use the podium mic. Why don't we just use the podium mic? Because that was working so well for Rebecca. So let's see here. Is that gonna?
Did you get it?
No. Yeah, help me with that, because that was working well.
Oh, it is working.
Is that working okay? Yeah, okay, so that's working better. All right. So I'm going to talk today about the effects of a couple of large geomagnetic storms. Mike Wiltberger likes to call them the St. Patty's storms of 2015-2013, which have quite a lot in common, you'll see as we go along. And the one in 2015 was the largest storm of the recent solar maximum. We measure that with a quantity which is an average of ground-based magnetic perturbations at low latitudes that's shown here. And I'm acknowledging my co-contributors here to this work. And my outline, I'm going to discuss modeling outer zone radiation belt electrons, which is a main focus of my group for these two CME shock-driven storms, and describe to you the extreme variability of the outer zone that can be modeled with global MHD simulations combined with test particle simulations. And then I'll also go on and discuss the fact that the global MHD simulations give us information on the electric and magnetic field in geospace, and we can use that information to do a different type of modeling of the radiation belt evolution, a diffusive transport calculation. So this is a nice figure that was provided by NASA and associated with the Van Allen probe satellites. I'll show you in the next figure those satellites that were launched almost 4 years ago to study this environment of space where MeV electrons and then closer into Earth, even higher energy protons are trapped in the Earth's magnetic field. And what you see is the artist's conception of the arrival of an interplanetary shock perturbing the magnetosphere, and one of the things I'll show you is that it compresses the dayside magnetopause, sometimes inside geosynchronous orbit, and it sets off these ringing oscillations called ultra-low frequency waves, which you can think of resonant modes of the magnetosphere that are excited by the arrival of the interplanetary shock. And then in addition to that, if there is a long period, as you'll see in the solar wind data that I'll show you, of southward interplanetary magnetic field, then given that the Earth's magnetic field is northward in the equatorial plane, that's conducive to the process of reconnection, magnetic reconnection, which enhances the efficiency of coupling of solar wind driving of this process of convection that's indicated by these arrows, where reconnected magnetic field lines on the day side are convected across to the night side. They reconnect impact in the tail and are convected earthward. During periods of strong driving where you have the southward IMFBZ and you have high solar wind velocity, as typically accompanies shocks, you have enhanced convection inside the magnetosphere. That is important because that convection brings particles in from the tail, which is the storage region of solar wind plasma that's been trapped in the magnetosphere. We're very fortunate currently to have the Van Allen probe satellites in orbit about the Earth. They're two identical, well-instrumented satellites that are in elliptical orbits near equatorial plane inclination, and they go out to 5.8 RE, so almost to geosynchronous orbit. And they're very well instrumented in terms of particle measurements and also fields measurements. This is a nice summary plot of the first 3 years of Van Allen probe's data, courtesy of Allison Janes over at LASP. That is taken with data from the relativistic electron-proton telescope. What is shown here is the flux of 1.8 MeV electrons, and these are averages between the measurements of the two spacecraft. I'll show you an example of where the two spacecraft were located when the shock arrived in March of last year. And this kind of plot, I'll show you several of these in a format where the vertical axis is the radial distance in the equatorial plane measured in Earth radii, and then you see time marching forward here. So these are 3 years beginning at launch. And what you'll see are these very strong enhancements in these MeV electron fluxes extending to lower radial distance associated with the arrival of a strong CME shock. So here's the St. Patrick's Day storm of March 2015, but you can see a similar one exactly 2 years earlier in March 2013. And there are others that you can go through and name that are associated with CME shocks, like this one in October of 2012. There are other enhancements here that are not associated with shocks, but other sorts of solar wind features. So for example, this one right here in early March 2013 was due to a high-speed solar stream event. So for those who don't live and breathe the radiation belts like I do, this is just a summary of the sort of periodic motion that particles trapped in the Earth's magnetic field have. And so you see the typical gyro motion about the magnetic field. There's bounce motion between hemispheres reflecting from converging magnetic field lines. And then there's also a longitudinal drift that's caused by the radial gradient in the magnetic field and the curvature of the field lines. And associated with each one of these periodic motions, there's a so-called adiabatic invariant in a classical mechanics sense. So think of integral of PdQ being a conserved quantity for periodic motion. And so in the case of the gyro motion, it's the ratio of the perpendicular energy to the background magnetic field. And there are invariants associated with the other two periodic motions. The first and the third are actually related to conserving the magnetic flux in the particle's periodic orbit. So the first invariant conserves the flux, magnetic flux in the gyro orbit, and the third invariant conserves it in the drift orbit. If you have any violations of, you violate these adiabatic invariants if you have variations in the fields on the time scale of the periodic motion. And so, for example, this is typically tens of minutes for the drift motion, even at an MeV, and very often the Earth's magnetic field changes on that time scale, and that invariant is violated. But there are higher frequency waves up around the electron gyro frequency that in turn violate conservation of the first invariant. So this is an artist's depiction of the radiation belt showing you the outer zone electrons, the inner zone protons, and it gives the illusion of this very steady configuration. But going back to this slide, you can see that it's far from steady when you focus in on the outer zone electrons. Okay, so what we have done, and with a great deal of help from Mike Wiltberger here, is simulate these various storm events using a global MHD model, the Lyon-Fetter-Mowberry model, which is what LFN stands for down here, is a global MHD code that solves the ideal MHD equations on the grid that you see here. And so this is the large-scale view of the grid going from 30 RE upstream to 300 RE downstream from the Earth, and this is a close-up of it. And so what we do to actually simulate the evolving electric and magnetic fields inside the magnetosphere is drive the upstream boundary of this code with measured solar wind parameters. Here at the L1 point, we can use data from the ACE spacecraft to describe the MHD fluid parameters as input into the code. And another spacecraft that we've been using lately is the Artemis spacecraft, which is in orbit about the moon. And so for a good portion of every month, it is out in front of the magnetosphere as well. The advantage of data from that spacecraft is it has much higher time resolution than the ACE spacecraft, and you'll see that when I show you the solar wind data. So here's a summary plot that shows you the solar wind data for the 2015 St. Patrick's Day storm. And so you see the arrival of the interplanetary shock over here. And this is the solar wind velocity, and it's plotted negative as it's increasing in magnitude towards the Earth. And then you see the east-west and the north-south component of the interplanetary magnetic field. And what's particularly noteworthy about this event is that there were 16 hours of southward IMF-BZ in which the magnetosphere was being strongly driven by this enhanced reconnection coupling on the day side, in addition to the increase in the magnitude of the solar wind velocity. So the impact that has in a global sense on the magnetosphere is seen in a parameter called DST, which is a measure of the perturbation of the magnetic field on the ground at Earth from 4 magnetometer stations near the equator. And if you have enhanced convection and you're bringing plasma in from the magnetotail due to that enhanced convection, the protons drift in one direction, the electrons in the other, and you get an enhanced ring current, it's called, of 100 keV particles, 10s to 100 keV. And that ring current produces a magnetic perturbation which is southward, whereas the Earth's magnetic field is northward coming out of the equatorial plane. So you get a reduction in the Earth's magnetic field measured at Earth. And so that's this blue line that you see here. It's the order of 220 nanotesla for this storm out of 30,000 nanotesla at the surface of the Earth. And it doesn't sound like a large perturbation, but for the electrons out there in space, it's a big perturbation where they're located, and the Earth's magnetic field is much weaker. So it affects the trapping, the orbits, and so forth of these electrons. Now, what's also plotted is a calculation of the equivalent perturbation at the surface of the Earth using the LFM code, and there are 2 different lines shown here. One is coupling the LFM code to a model of the ring current that includes the energy-dependent drift physics of the ring current. So the ions drifting one way, the electrons drifting the other, and the drift being energy-dependent. Whereas the top line here does not include coupling to the so-called Rice convection model. This is the same type of plot for the storm 2 years earlier, and so I won't dwell on that. Now here's what happens to the electrons when you have one of these events. So this is from the Relativistic Electron Proton Telescope on Van Allen probes, and these are 3 different fairly high energy channels. And you see that when the shock arrives, you get a dropout influx as the first thing that happens. And this is, I'll show you, is due to inward compression of the magnetopause and basically loss of particles to the magnetopause. And then you get an over-recovery relative to what you had before, and that was evident in those summary plots. And you'll also see that you get acceleration to higher energies than you had prior to the arrival of the shock, and that there's a delay in the time that it takes to accelerate particles to higher energies. And this is something that you would expect both for local acceleration or by radial transport. It just takes longer to get particles up to higher energies. This is a plot that's intended to show you that the MHD model does a very good job of reproducing the location of the magnetopause. And so this is a comparison between the MHD model and a phenomenological model based on assimilation of a lot of data into a model that's parameterized by solar wind conditions. And so you can see that for this storm, the magnetopause is coming inside geosynchronous orbit at 6.6. So here's the result of putting test particles into those MHD fields. This was work that was done by Jan Peral, who was a postdoc here working with Mike. And on the left, you see the result for the 2013 storm, and on the right for the 2015 storm. And what's being plotted here is simulated flux in two different energy channels for the two storms of the REPT instrument. And again, it's in this format of flux as a function of radial distance plotted as a function of time. And this black line you see plotted here is the location of the magnetopause as computed from the MHD code. The dashed line is the location of geosynchronous. And so what you see down here, the solar wind data is plotted again, and you see that with arrival of the interplanetary shock, the magnetopause is pushed earthward, and particles that were previously trapped at higher radial distance are now lost to the magnetopause. And that loss, if you go on over and take a look at the March storm, continues. This is only a short snippet of maybe the order of 3 hours of the storm. But the loss is continuing, and it's occurring even inside the location of the magnetopause. And I'll argue as we go along that there are oscillations, these ULF wave oscillations that cause a diffusive transport of the electrons to the magnetopause, even inside the location of the magnetopause. So this is the main reason for this dropout that you saw back here. That initial dropout is due to radial transport as the magnetopause is pushed inside geosynchronous orbit. Okay, now the next thing I want to talk about is the energization, because you see that there's a recovery that occurs after that initial loss. And so this is from a different type of test particle simulation, whereas the previous one started with already trapped electrons and looked at their loss to the magnetopause as it moved earthward. This one is following the injection of test particles from the night side. So you see the day-night indicated here in the little Earth. And Brian Kress, who is over at NOAA these days, developed while he was at Dartmouth a three-dimensional test particle code for injecting particles into the MHD fields. And he does that from the night side, and they are transported earthward by that convection process that I described earlier. And then, as electrons come earthward, they begin to experience this gradient curvature drift that causes them to drift around in this direction. Now, what you see happening is that some of those particles are being trapped, and furthermore, because they're coming into a region where the Earth's magnetic field is stronger, and they're conserving that first invariant, they're conserving the ratio of the perpendicular energy to the magnetic field. Since the magnetic field is stronger closer into the Earth, their perpendicular energy is increasing. And so you can see that in this color bar over here. You start out with 100 keV sorts of particles out in the tail, tens to 100 keV. And then by the time they come into the inner magnetosphere, they're energized up to the MeV energy range. So Brian, I'll show you a movie of this, but Brian has shown that this is a substantial contributor to the outer zone electrons, just the enhanced convection that you get during storms. So my postdoc, Zhao Li, has gone on, and that was from a storm in October 2012, has gone on and modeled the storm in 2013. So she has similar sorts of plots. These are coarser snapshots here. And instead of plotting the energy like Brian did in the previous plot, she's just plotting the flux here. But I want you to take note of the white circle that you see here, which is geosynchronous orbit. And what she's showing in these snapshots is that you're getting particles well inside geosynchronous orbit. And this was for a particular energy range. What we actually quote is the first invariant. So this was for 1,000 MeV per Gauss electrons, which corresponds to maybe half an MeV at geosynchronous orbit. So I actually have a movie of this, which is just a poor man stepping through 1 hour sequences. And so it's somewhat, coarse-grained. A better movie is the one that Brian produced for the 2012 storm. And I'll run through this a couple of times. What he has running around here in circles, besides the injection of the electrons, are the two spacecraft. So you can see the GOES spacecraft is at constant radiolocation, and Van Allen probes is swinging in and out. So let me run that again. Because Brian did a very nice comparison over here on the left between the modeled and the actual measured flux at GOES in one of the energy channels of the GOES spacecraft. And similarly down here, he's comparing the modeled and measured flux at Van Allen probes in one of the Van Allen probes energy ranges. And so let me run through that again. Because I want to make the point that the axes over here are orders of magnitude. So the code is doing a very good job of reproducing the flux as Van Allen probes moves in and out. And the reason for these horns, we call them here, is simply because the Van Allen probes is going in and out of the radiation belts rather than staying at a constant radiolocation like GOES. So now we ask the question, what physically is doing the transporting? And I've argued that, and Brian would argue, that the convection electric field is doing a fair amount of the transport. But it is not a monolithic, uniform dawn-dusk electric field as people draw in the very simple cartoons. So this figure right here from Zhao's paper looks down on the equatorial plane and it plots the azimuthal electric field. And in a right-hand coordinate system, the azimuthal electric field would be positive counterclockwise. And so the fact that it's blue and negative means that it is clockwise. And that is in the opposite direction, you'll remember from the earlier figure from Brian, that electrons are drifting. And so that's good, because that means that if the electric field is opposite the drift direction of the electrons, due to their negative charge, they're gaining energy from that electric field. And as they gain energy, conserving the first invariant, that causes them to move radially inward. So I thought I'd show you a few more figures of this kind of localized azimuthal structure. Here you see it in the electric field looking down on the equatorial plane. And this is from a series of simulations that Mike did, where here he's plotting BZ instead of E phi, but they go together to give you an E cross B fast flow of particles coming in from the tail. And here Mike cranked up the value of the interplanetary magnetic field as you go from one figure to another, 1, 2, 3, you're increasing IMF BZ magnitude. And you can see the localized structure that you get in BZ, and likewise you get in E phi in these figures. And then this one right here goes through the same increase from the same paper by Mike, showing you the fast flows. This is flow velocity, so this is a combination. You get these fast localized flows. These were called bursty bulk flows when they were first discovered in the satellite data, back in the 70s probably. So this is how the radial transport works. It is not this monolithic uniform transport, but it tends to be localized where the electric field and so on is more intense in the MHD fields. So the effect, as I said, is that you have inward transport of the electrons due to these enhanced localized E phi regions. And what Zhao has done is pick 10 electron sample out of the hundreds of thousands that were injected from the tail, and shown here that over the course of the storm that she's simulating, a subset of those electrons are transported radially over many RE very rapidly. And then there is this continued diffusive transport over a longer time scale. And that is due to the ULF waves, the ultra low frequency waves that I'm going to describe next. So you have this period of very rapid radial transport, and then you have continued diffusive transport. So let me get on to talking about the ULF waves. This figure is from its analysis of data from the Electric Fields and Waves instrument on the Van Allen probes. So it actually has, I think it's the order of 100-meter tip-to-tip booms. These are very long booms in which they measure the potential difference between the ends of the booms in 2 orthogonal directions in the spin plane. And they also have a spin plane measurement of the electric field, or spin axis measurement. And so it's plotting the azimuthal electric field component, and Fourier analyzed here. Here's the arrival of the interplanetary shock. And prior to the arrival of the shock, you see that there's power around 20 millihertz that persists after the shock arrives. When the shock arrives, you have this, sort of like step function that gives you a lot of power across a whole range of frequencies. But what persists at later times is power down in the few millihertz range, which corresponds to the drift frequency of MeV electrons at GEO. And so what this kind of ULF wave power is going to do is it's going to violate conservation of the third invariant, because this invariant associated with the drift motion is the electrons are going to see fluctuation in the electric and magnetic field on a time scale that's comparable to their drift period, and so they're not going to be able to drift on have a constant orbit in radial distance. So this power is going to cause what we call radial diffusion. I thought I'd just show you where the Van Allen probes were located when the St. Patrick's Day shock hit, and so they were both over here on the night side. And they are chasing each other around. They have just a slightly different apogee, so that every once in a while they lap each other and the separation between the spacecraft changes. But for this particular event, they were pretty much 180 degrees apart on the night side in this looking down on the equatorial plane view on the left. Okay, so this is a nice figure from a former CU PhD student, Seth Claude Pierre, in which rather than drive the MHD code with measured solar wind parameters upstream, he did a number of experiments where he ramped up the solar wind velocity from 400 to 600 kilometers per second, from 400 to 800 kilometers per second. And he showed that you get increased ULF wave power, and so that's what's plotted here. It's the power in the millihertz frequency range in the azimuthal component of E, and it's penetrating deeper into the magnetosphere, and you have more power as you go to higher solar wind velocity. So this is a different experiment from hitting the magnetosphere with a shock. But the main reason I pulled this figure, and it was actually from a set of slides from his advisor, Scott Elkington, is I hope you can see, and it isn't totally chopped off over here, that there's an electric field vector that's going up and down, and it's oscillating with the same frequency that the electron is moving around. And so the electron sees a variation in the fields on the timescale of its drift period, and this causes it to undergo a random walk in the radial direction, which we can describe by diffusion. And so how do we describe things by diffusion? Well, we have to have a diffusion equation. So this is just a one-dimensional diffusion equation, kind of like you have for heat in a pot on a stove. It's describing diffusion in the radial direction. If we focus on particles confined to the equatorial plane, then they have no bounce motion. And if we average over their gyration period, which is occurring on a much faster time scale than these low frequency fluctuations, then we can write just a one-dimensional diffusion equation in this parameter L, which is radial distance measured in Earth radii. And then we add a loss term over here, which takes into account the fact that electrons get lost to the atmosphere. So there's a rate at which they're lost to the atmosphere due to collisions and due to scattering from higher frequency waves. Whereas this part of the equation will describe radial loss, for example, to the magnetopause or to the inner boundary. So what we need in order to implement this equation is a diffusion coefficient. And that can be calculated from knowledge of the fluctuating electric and magnetic fields, either from observations or from our global MHD simulations. And the problem with doing it from observations for any single event is that we never have a very dense measure of E and B throughout this large volume of space. You can get statistical information over a long period of time, but for a given event, we just don't have very dense measurements. And so what we're doing now is using the global MHD simulations to calculate the spectrum of electric and magnetic field fluctuations and plugging those into calculating a diffusion coefficient to see how much of this can be described as diffusion. So I don't want to dwell too much on this slide other than to say that this is what the ULF wave power in the MHD simulations looks like as a function of radial distance before and after the shock. So you can see there's a lot more power after the shock arrives than before. It is concentrated down here in, this is actually plotted as a function of what's called azimuthal mode number. So if you can think of in terms of the number of azimuthal wavelengths that you would fit around a circle. And you can see that most of the power is concentrated down around m equals 1, which corresponds to a day-night distortion, but there's still some power at higher azimuthal mode numbers. And so this is the power that we have to plug into those diffusion coefficients then to calculate the rate of radial transport. So HAO has done this using the MHD simulations driven by the actual measured solar wind input for this storm in 2015. And so this is a plot of the radial diffusion coefficient, and it's measured in units of inverse days. And for example, you wouldn't want to look at this and see 100 or something, because then it would correspond to a process that was starting to be faster than diffusive. It would be occurring faster than the drift period of electrons. And so it's separated into these two different diffusion coefficients that I mentioned back here. One, the top one associated with electric field fluctuations, and the bottom with magnetic fluctuations. So think E phi and BZ that go together. And you see that the coefficients associated with electric field fluctuations are considerably higher than magnetic fluctuations, which is the set down here. These are plotted for, you can think of this as 3 different energy ranges, so 3 different values of the first invariant. And you'll notice that it's relatively independent of energy or first invariant. Then the next thing that's really obvious is that it goes up by orders of magnitude during the storm, during the main phase of the storm, as we call it. That previous slide shortly after the shock arrived right here, and for most of the rest of the day, the ULF wave power and therefore the diffusion coefficient is strongly enhanced relative to prior to the storm. The following day, what we call the recovery phase, where that the ring current is relaxing in that plot of the DST parameter, you see that the diffusion coefficient is staying relatively constant. So you have this big burst, and then it's staying relatively constant, but it is still enhanced significantly relative to what it was prior to the arrival of the shock. So let me describe then what this does to the radial density profile, the so-called phase space density. If you have diffusion and you have a source at high radial distance, which is what you have in the storage region in the tail, the so-called plasma sheet, the source population that's being transported earthward, then any kind of radial transport is not going to give you a peak in phase space density, but if you keep feeding it, it will enhance. As you will see when I show you the actual data from Van Allen probes. It will give you a radial profile that looks something like this. And it will enhance the phase space density at lower L values. Now, another mechanism for changing the phase space density, as I mentioned earlier, is to violate conservation of the first adiabatic invariant. So if you have waves with frequencies up around the electron gyro frequency, if an electron sees a right-hand circularly polarized electric field in its frame of reference, it can get accelerated by that electric field if it sees a constant electric field that's rotating around at the same frequency that it's gyrating. So that's basically the mechanism for local heating by so-called very low frequency waves, Whistler waves. And what that will give you, if it's occurring at a particular radial location, and there's evidence that this happens, is an actual peak in phase space density that you don't get from the radial transport mechanism. Now, there are other ways to get peak. An important way to get a peak in phase space density is if you have a sudden drop in the flux at the outer boundary, or the phase space density at the outer boundary, due to inward motion of the magnetopause. That will give you a peak in phase space density as well. So just seeing a peak in phase space density is not by itself evidence for local heating, because you can get that by changing the outer boundary. Okay, so this is a nice plot that Zhao made from the actual Van Allen probe's data. And it shows a number of interesting things. So it's an interesting format. The color is showing you time going from blue to red over the course of the 2 days of the storm. And so the first profile you see is the phase space density of 1,000 MeV per Gauss electrons right at the beginning before the interplanetary shock arrives. And you can see that there is a very mild peak in phase space density that could be attributed to the motion of the outer boundary, which is the magnetopause, which is happening all the time due to solar wind pressure variations. Another thing to notice is the location of this, the location in this parameter L star. Now, L star is related to the radial distance in the equatorial plane in units of Earth radii. But instead of being given strictly in terms of Earth radii, what that parameter is doing is it's conserving the magnetic flux inside a particle drift orbit. So if you go from here to, let's go here, which corresponds to the next orbit later, and so that's occurring at this time right here. This is the apogee of Van Allen probes in L star after the shock arrives. This is the apogee before it arrives. The apogee is still at 5.8 RE, but the whole magnetic field configuration has compressed. And so because of that, the apogee of the satellite is actually at a lower L star. It has to be in order to conserve the magnetic flux inside a particle drift orbit if you've significantly compressed the magnetic field, as you do when the interplanetary shock arrives. So this next orbit right here starts at apogee, just like this one did, but it's drastically dropped in phase space density because you've lost a lot of particles to the magnetopause when the shock arrived. And then you can march on up to subsequent orbits. And so the next one that's really interesting is this green one right here, which occurs right around midnight on March 18th. And that has an actual peak in phase space density. So that is indication that some local heating has occurred to produce that dramatic peak in phase space density. But if you go further on in time, to the end of the 19th of March, you see that the magnetosphere is relaxing a little more, and so Van Allen probe's apogee is now out here again instead of being here. And now you have this monotonic profile, essentially, and it's orders of magnitude, or at least an order of magnitude, I guess, higher in phase space density than what you got from the local heating. Yes?
What is the K value for this phase density calculation?
It's the lowest one that was available from the data.
It's close to the...
close to the equator, right. So, so I guess the point I want to make is that, yes, there is local heating going on here, but you are continuing to feed particles in from the plasma sheet due to radial transport. And in fact, that's dominating the order of magnitude increase that occurs over later time. So it's the latter that we model because our model does not include the local heating with the very high frequency waves that aren't resolved by MHD. So what Zhao then did was take the radial diffusion coefficients that she computed from the MHD simulations, and she plugged it into solving that one-dimensional radial diffusion calculation. And I'm not sure if it's being chopped off over here, but this, can you see the L star values over here? Probably not. I can see them on my screen, but I don't think you can see them. But this corresponds to L star of 6 here, and this right here is 5, and this is 4.5. So this is emphasizing the fact that the apogee of Van Allen probes was at 4.5 at midnight on the 18th of March, right after you had the local heating. And so what Zhao has done is in order to solve a radial diffusion equation, you need some boundary conditions. And so she takes as her initial radial profile the one that was measured by Van Allen probes on the orbit that went through midnight on the 18th. And there's that peak in phase space density that you saw as a green line on the previous plot. And then you also have to feed in an outer boundary condition. And so what she feeds in is the measurement of the phase space density at apogee. And she uses the diffusion coefficients from the MHD simulation, the average value on the 18th, when they were relatively constant and elevated, higher than they were before the storm, but not as high as they were during the main phase of the storm on the 17th. And she solves the radial diffusion equation then and marches it forward in time. And so she's continuously updating this outer boundary here by whatever the measurement at apogee is from Van Allen probes. And apogee is changing, so it starts off here at 4.5, but over the course of the 12 days that she's simulating, it's moving outward. And so I marked here the lower boundary and the upper boundary of apogee over the course of the 12-day simulation. So the real question is, how does this compare with the ongoing measurements? Because all through this time, the Van Allen probes are going in and out, in and out, in and out, and so you can do a subtraction comparison between how well the radial diffusion code is doing relative to the actual measurement. And that's what she's done over here on the right. And so green is very good. Green is go. Because that means that that's consistent entirely. It's a 100% agreement between the calculated phase space density and the measured phase space density for that particular orbit. And you can see that, at earlier times back here, before the 22nd, the radial diffusion calculation is underestimating slightly relative to the measured phase space density. And that's because there is some ongoing local heating occurring at that time, which the code does not include. But it's actually doing a very good job of reproducing the measured phase space density over this time period. And so how good a job is it doing? We compare it with radial diffusion calculations that have been done earlier, so we might as well compare with our own. This is a simulation that Zhao did for the storm back in 2013, March 2013, and here she simulated the entire month of March. That was the month in which there was that high-speed stream-driven storm that I mentioned earlier when we looked at Allison James's summary plot. And then you see the CME-driven storm that occurs here on March 17th. And then down here is that same type of difference plot. Now, what she's using for the radial diffusion coefficients in this case is not from MHD simulation. So Mike hasn't run, even we might ask him, but I don't think he would, run the MHD code for the entire month of March 2013. So instead, what she did back at the time of this study was use a standard model that is used by many groups for the radial diffusion coefficient, which is based on a parameterization of geomagnetic activity. It's called the KP index, and if you go to the SWPC website and look at their satellite environment summary plots, they'll give you the proton flux, the electron flux, horizontal component of the Earth's magnetic field, and KP. And so KP is a measure, a 3-hour average of geomagnetic activity based on mid-latitude magnetometers, and it's a very crude measure of the level of geomagnetic activity. And so a model has been developed for what the diffusion coefficients are as a function of KP, as a function of geomagnetic activity globally. And so if I'll switch back and forth between this figure and the previous one and argue that the agreement is not as good when you use these global parameterized diffusion coefficients that many groups are using as compared to what you get on the right when you're using the MHD simulations to calculate the diffusion coefficients. So that's really the punchline there, that an improvement is made using the diffusion coefficients from MHD relative to these, more than a decade, 2000, 16-year-old diffusion coefficients. To summarize what we're doing here, we sort of have two approaches. One is MHD test particle simulations, and I showed you work that Brian Kress did and Zhao also did, where you inject particles directly into the MHD fields. And we can do that for about the length of a geomagnetic storm, so a couple-day simulation. But to do a longer time interval, you have to run the MHD simulations for a very long time, burn a lot of computer time to imagine month of March, or even the 12 days following the St. Patrick's Day 2015 storm. So we do these MHD test particle simulations for the main part of the storm in order to make some direct comparisons with how well we're doing with the diffusion simulations. Neither one of these includes the local heating because they both use the MHD framework, which does not describe waves up around the electron gyro frequency, so it doesn't include the local heating. But we have, I have a student here in the audience whose, thesis topic is to compare how well the MHD test particle simulations do relative to the radial diffusion simulations, which you can do for a longer period of time. Now, one thing we can show with the test particle simulations is the effect of the magnetopause compression, the effect that causes the prompt loss that's seen in all major storms that are driven by CME shocks. Another thing that Zhao compared was a comparison between plasma sheet injection versus retention of initially trapped electrons. And it turns out that the results are not very sensitive to including the initially trapped electrons for these big storms. You get such a flushing of the outer zone, a dropout in flux or phase-space density, that you can pretty much describe the outcome in terms of plasma sheet injection alone. So what we have done then to go on from there is to calculate diffusion coefficients from the MHD model and use those diffusion coefficients in a radial diffusion calculation. And what we found for the diffusion coefficients in itself is interesting because you can compare it with several other studies that have been done using satellite data to calculate the diffusion coefficients by measurements of electric and magnetic fields, or ground magnetometer measurements, which give you a more global sense of what the magnetic field variations are like. But then you have to make some extrapolation from that to the equatorial plane. So our results are consistent in several aspects with what has been found in these experimental studies, that the diffusion coefficients are relatively energy independent, and that the electric field diffusion coefficient is larger than the magnetic diffusion coefficient. We're building confidence that MHD captures a great deal of the physics of these storms in terms of describing the enhanced convection that you can then trace with the test particles, and in describing the diffusion coefficients that you can use in these radial diffusion calculations. So I think that's it.
Questions?
Yes.
I have two questions. Mike, you are here, you don't want to answer. Both questions about the MHD model.
Yeah.
And I was very impressed this RFN plus RCM, couple of RCM. That really reproduced this March 17, 2015 storm DST very well.
Yes.
But did not reproduce that March 17, 2013 well. So I don't know, was there any comment about that one from that RCM couple that reproduced the last year's DST very well? That was impressive.
So you want me to go back?
Yeah.
You want me to go back,
Sure.
way back to that slide that I spent no time whatsoever on? That one right there.
See, this is,
so you know.
This is 13.
Yeah. So you're not happy with this down here, is that right?
Right, but I'm very impressed by the go further forward. You see, that was very
that one you liked
very much,
and this one you didn't like so much. Well,
I just want
it turns out that Mike is
between the orange and green lines.
Yeah, the emphasis is the orange and green line, not the green and blue line that you're focusing in on. That's the key point of that bottom panel. So the green and blue, you know, the measured blue, or the measured is blue, is that
Yes,
right?
yes.
And LFM-RCM is green. And so those are agreeing pretty well, and the orange not so much, without including the ring current physics. Mike is actually rerunning the 2013 storm as we speak, because this was done at lower resolution than the 2015 run, so he's rerunning it at the same resolution, and he's extending it to 2 full days so we can see the recovery phase of the storm just like we saw here. So I wouldn't pass too much judgment on this figure. There'll be an updated version at the same resolution and run for 2 days.
Okay, very good. So Mike was not happy either. Okay.
Yeah.
So my second question is from DST wise, you're talking about this RCM, but then you're the tracing the particles. I saw some of your figure. The tracing particles actually on the field generally with the mix.
Yes.
So how different they are in a
Right. Yes.
If you have same source population, then I can guarantee the.
Yeah. So so as far as the run that Brian did, he did LFM mix. He was not happy with the agreement at GOES. See, this is at the ground. He was not as happy with the agreement at GOES with LFM mix as he was. I mean, with LFM RCM as he was LFM mix for the October storm.
Yeah.
So he chose the one that had the better agreement with GOES. You know, he's over at NOAA. No, he did that before then, but he chose that one. So that's one issue. And then the other issue is that there is an ongoing issue of LFM-RCM coupling when you are blasting the system as hard as you are in these storms. I think it's still a work in progress. Is that fair?
Yeah, we have another curve to put on that line, which implements some enhancements to the ionospheric conductivity model, which helps stabilize the high-speed flows that are a problem for LFM-RCM coupling. And so we continue to get good agreement with the DST and improve the quality of the fields at geostationary and in the magnetosphere. And in fact, that's what I'm running for you right now for these events, so we can do a full-up field push in the LFM-RCM space.
Right, but Brian took the empirical approach. Better agreement goes with LFM mix, so those are the fields he used.
Very good.
Yeah.
Well, back to Shinlun's first question, so it seems like a fair question. I mean, it's actually amazing how well the simulation is tracking the observed DST, the time dependence early on in the storm. And then you go to the 2013, and its main flaw is that it's not tracking that early behavior of the storm. I mean, it does a reasonable job in the late phase.
Right. Yeah.
But so what is it about the simulation that?
Well, so this is lower resolution again compared to this one. So this is like quad res, right, Mike? And this is double res. So you've got the fields now to give me this plot for half a day at quad res. So let's take a look at it this week. No, so I don't know. I don't know what it's going to look like. It's kind of apples and oranges not to be looking at the same resolution, isn't it?
It matters a lot for this thing, because as you increase the resolution, the quality of the region 2 currents, regardless of including the ring current model, improves dramatically, and so you're going to get a better region 2 setup in the higher resolution results.
Just comment on Bill's question is that the earlier phase of the jump in the DSTs, that's actually coming from the compression of the shock.
Right.
So a higher resolution model will resolve the currents near the shock much better than the lower resolution, so you can have a better DST in the time history of the first one.
Yeah.
I do have another question.
Mm-hmm.
Is that so when you calculate the radial diffusion coefficients using the ULF wave power modes from MHD, do you use all the wave modes number to 20 as you show?
We use let's see here if I can escape and go down. I'll show, yes we do, and we use I'll show you the ones that we use. I decided not to put this in the talk because it gets into a little bit of detail, but let's see where it is. There it is, I see it, 52, slide number 52. So there's a whole bunch I spared you. So this is showing at a fixed radial location, geosynchronous. It's showing the frequency spectrum as a function of azimuthal mode number, and those two lines, the white and the black, correspond to omega equals m omega drift for particles of different first invariant. And so each one of those squares is included in the sum over here to get the total power.
So the reason I'm asking is that are these from the double resolution?
No, because this is the
So-
2015 storm, which
So
is the
it's
quad res.
Quad res.
2015.
Yeah, the 2015 is quad res because we've moved on. And the 2013 simulations, which were done 2 years ago, was done at double res at that time, but I asked Mike to go back and rerun it at the same
So this is
res.
the higher resolution.
Yes,
So quad res has about 200 cells as a mucilate in
Mhm.
the equatorial plane. So mode of 20 means that you have about 10 cells to resolve a structure.
but we don't have much power out here, and so, your power is back here, and also that's what's satisfying the resonance condition, so that's what you need.
So you have 192 cells with quad resolution, so you can go up to m equals 96.
Right, but there's not much power out there, as you know.
Right, anything further than.
Right.
Yeah, because the reason I'm asking that when you're approaching to a structure has like 5 to 10 cells to resolve that, it's pretty risky, but you don't have much power there
So,
anyway, so.
So I want to say this MHD, this is the best we can do. If you do talk about physically based MHD model, give you particle structure, a field, and then you're tracing the particle, give reasonable, source population based on measurement and larger aperture. I feel this is the best we can do. I really, really feel like it, but I'm still wondering, this LF mix. If you have LFM rise, how different this field would be.
right,
If you have
right,
same
yeah.
spectrum, we would love to see this
Side by
thing.
side comparison
Yeah,
of the
so
two.
was a model
right.
dependent or
Yeah, and the fact of the matter is that there's cause for concern with the LFM RCM fields when you're hitting it this hard.
but then they reproduce DST so well.
Yeah, well, there's a difference maybe also between the average, which is what DST is, and the fluctuation spectrum, because the fluctuation spectrum is picking out all of the smaller scale structure, coming in from the tail, and Scott, as you know, still has questions about that, how well it's resolving that. Art.
So this modeling does a very good job at explaining the variation between L star of 5 to 6 and inward.
Yeah.
But you start from observations.
Yes.
And
Yes.
what do we know or don't know about how you get the needed energy spectrum and so on?
Well, the real
structures?
problem is what we need is phase-space density at a higher radial distance. And so I have, wrung the necks of my Los Alamos colleagues trying to get geosynchronous data for input rather than using the apogee of Van Allen probes, because the apogee of Van Allen probes is way down at 4.5 for these big storms. And it would be nice to be further out yet. For some storms, we're fortunate that Themis is out there, but what is available is a statistical model based on Themis one can use, and HAO has done that. But we are lacking the measurement of, another student I had, Fei Chu, who spent quite a bit of time here, showed that the single most important factor is that outer boundary condition and the variability of that outer boundary condition. And so if we had better information, that would improve things. Yeah.
Any other question? Let's thank Mary again.